All right, guys, so we ended that last part looking at the magnetic force diagrams. So it told us that the distance away from the object, the material, the size, and the orientation of the magnets all matter. So what these pictures show us is that the longer the arrow, the stronger the force is. It also shows which way the force is going. So if you look at distance, it shows that there's a longer arrow here than over here. So the closer this object is to the magnet, the stronger the magnetic pull or force would be than on this object over here. Now, the material of the magnet also matters. So neodymium is more magnetic than ceramic. So that's why we see a force for both of them, but the neodymium is stronger. So it's going to have more of a pull to a magnet than the ceramic would. And then size as well. So we see that the bigger the magnet, the stronger the pull. And then orientation. So orientation means which way the bar magnet is facing. So is it north and south closest to each other, and that way they would be attracted to each other, or is it south and south facing each other, and that way they would be pulling the opposite direction? So on your journal, when it asks you to draw a force diagram, you can use one of these examples as well. Make sure you label which type it is. Is it a distance one, material, size, or orientation diagram? Okay. Magnetic field. Like the electric field that surrounds a charged particle, a magnetic field surrounds a magnet. This is the area around the magnet where it exerts a magnetic force. So kind of like it's an invisible area around this magnet. The figure below shows the magnetic field surrounding a bar magnet. Tiny bits of iron, called iron filings, were placed under a sheet of glass. When the magnet was placed on the glass, it attracted the iron filings. The pattern of the iron filings shows the lines of force that make up the magnetic field of the magnet. The concentration of iron filings near the poles indicates that these areas exert the strongest force. I'm going to zoom in a little bit. That's a pretty cool picture, guys. So it shows like the direction and the area on where these forces are. And it also shows you where the stronger forces are because there's more iron filings in that area. So this was all like happened naturally when the bar magnet was set there. And we've kind of seen things like that before whenever we were using our bar magnets and iron filings. When two magnets are brought close together, their magnetic fields interact. You can see how in the figure below. The drawings show lines of force of north and south poles attracted to each other, whereas those of two north poles repel each other. The animations at the URL below show the magnetic field lines change as one or two more magnets move in relation to each other. So I'll post that if I can get it to cooperate. Maybe we can see the animations. So this shows that we have two bar magnets here, a north pole and a south pole. And it shows like a connection between the forces here that are attracted to each other. And you guys see that whenever we pull, they pull together. But whenever it's a north and a north, they are repelling away from each other. See how they're kind of like trying to avoid each other, pushing apart. Magnetism and materials. Magnetism is the ability of a material to be attracted by a magnet and to act as a magnet. You use magnets every day. No doubt you've handled refrigerator magnets like the ones in the figure below, and you probably know firsthand that they stick to a metal refrigerator, but not to surfaces such as wooden doors and glass windows. Wood and glass aren't attracted to a magnet, whereas the steel refrigerator is. Obviously, only certain materials respond to a magnetic force. Some magnets are hidden within machines. For example, computers, which use magnets in their processors, monitors, and speakers. Cell phones also use magnets in their displays. What makes a material magnetic? Iron nails are not natural magnets, but are easily attracted to magnets and can easily become a magnet. Why is this the case? There are large areas where the north and south poles of atoms are all lined up in the same direction. These areas are called magnetic domains. Generally, the magnetic domains point in different directions, so the material is not magnetic. That would be like here if they're all kind of pointing off in random different directions, so it's not magnetic at this point. Okay, here we are. This is the case with the iron nail. All the magnetic domains in the nail point in different directions. However, the material can be magnetized by placing it in a magnetic field. When this happens, all the magnetic domains become aligned and the material becomes a magnet. This is illustrated in the figure below. So that would be like this. Once it becomes magnetized, all those arrows, all those domains point in the same direction. The ferromagnetic materials previously discussed, like iron, cobalt, and nickel, can be magnetized in this way. So they somehow have to be aligned by an outside magnetic field in order for them to become magnets. Temporary and permanent magnets. Materials that have been magnetized may become temporary magnets. An example of a temporary magnet is described below. We saw this before in a video. If you stroke the iron nail with a bar magnet, the nail will become a temporary magnet. Its magnetic domains will remain aligned, so like this, all in the same direction, even after you remove it from the magnetic field of the bar magnet. Temporary magnets can be demagnetized, however, if they are dropped or heated to high temperatures. These actions move the magnetic domains out of alignment and they will lose their magnetic capabilities over time. So, like a nail by itself, if we haven't put it in the field of a magnet, is not magnetized. So, it can't attract, it doesn't do anything like that. But, like we've seen before and what we just read, if you were to rub the bar magnet on it for a period of time, it becomes a magnet. So, that's whenever these domains turn from scattered and random to all organized in one direction. And that's when it can become a magnet. It can lose its magnetic properties, though. Like it said, if it's dropped or heated, then they aren't aligned anymore. Paper clips become temporary magnets when placed in a magnetic field. An iron nail becomes a temporary magnet when stroked with a bar magnet. All right, guys, that's the end of our reading. So we're going to go back to the journal. I'm going to go back to your journal and you're going to answer questions on 7 through 8. So I'm going to pull that up as well and throw another video in Google Classroom to show, just to kind of talk through some of those questions that you're going to be answering. All right, guys, have a lovely rest of your day.